Hello, so today we are going to continue on problems from Leetcode Daily Challenge. So today is April 1st problem, shortest path in binary matrix. So what this problem basically tells us is we have an n by n matrix grid, and we want to return the length of the shortest clear path in this matrix. And if there is no clear path, we want to return -1. But what do they mean by clear path? Well, it's just a path from the top left cell, right? So at 0, 0 to the bottom right cell, okay? Such that all the cells that we visit in that path are 0. And the way we visit cells is we check the 8th directionally connected cells, okay? And what we want to return at the end is just the length of a clear path. Basically just the number of cells we visit in that path, okay? So let's take a look at an example, and also just to clarify here, they mean by 8 directionally connected, they mean like up, down, left, right, and then these two diagonals and these bottom two diagonals, okay? So with this we have 1, 2, 3, 4, 5, 6, 7, 8 directions, right? And so if we take a look at this first example with this grid here, we start from this position and we want to go to this position, okay? So the shortest path is this, right? We will only touch cells with value 0. And what's the length here? Well, the length is basically the number of cells we traverse. So it's 1 and 2, okay? You can't go here, right? Because there is a 1. And you can't either go here because there is a 1. And so the path is just 2. If we take a look at the second example, the shortest path is going from here to here is basically to go right, diagonally like this, and then go down. And so how many? We have 1, 2, 3, 4. So we return 4. Okay. Now another possible path is like this, but this path is 1, 2, 3, 4, 5, length of 5. We can't go to these values of 1. We have to go only through zeros, and so that's why also here the only two paths are this or this. Okay, and this one is the shortest, so we return it. I hope that clarifies it a little bit. Now, the dimensions are not too big. N can be up to 100, and the matrix is n by n. So at most we have 10,000 cells. So yeah, let's see how we can tackle it. Okay, so let's see how we can handle it. Well, the problem asks us to define the length of the shortest clear path, okay? So we want the shortest clear path. Well, whenever you are asked to do this, then you should immediately think about BFS, because that's what BFS is for, exactly finding the shortest path. So here, then we can just use BFS and just go through each node and then go through the neighbors of each node. Now, how to find the neighbors of each cell? So let's say we have a cell ij, because we have a grid, right? We start from the top left, we want to go to the bottom left, and then we traverse nodes to reach the bottom right, okay? So how do we determine for each of these nodes the neighbors? Well, it says 8 directions, and so the 8 directions are just going right, which is going to be I plus 1. So going right is the column that increases by 1, so I, j plus 1. Going left is I, j minus 1. Going up, which is going to be the previous row, so I minus 1, j. Going down, which is going to be the next row, so I plus 1, j. Going diagonally, which are going to be just I plus 1, j plus 1, and then I minus 1, j minus 1. So this one is going to be I minus 1, j minus 1. This one is going to be this one is going to be I plus 1, j plus 1. This one is going to be I plus 1, j minus 1. And then this one is going to be, this one here is the top row, the row before that, so it's I minus 1, but it's the next column, so it's j plus 1. And these are the 8 ones, right? So we have 1, 2, 3, 4, 5, 6, 7, 8, right? So we can just go through these neighbors, right? And the problem also says that clear path, which means the values have to be equal to 0. Okay, so we will only go through to a node that has the cell value equal to 0. Okay, so that's another thing we'll make sure to do. And then with a graph that you are traversing, you should always think about how do you mark visited sets so that you don't visit them again. The easiest approach is just to use a visited set, right? And in that visited set, we can just add the cells that we visit. And then when we are visiting a neighbor, we won't visit it if it's already visited. So we'll check if it's invisited, we'll skip it. Okay. So that's pretty much it, what you need for BFS. Now, how do we determine the length of the path, right? Well, just in our BFS queue, we can just add the coordinates, of course, but we also need to add the number of cells we've visited so far. Let's call it count. So that at the end, if we are at the last cell, which is just at row r minus 1 and c minus 1, this is being the number of rows and this is the number of columns, then basically at this cell we can just get the count, because each time we visit a neighbor we can just increment this count by 1 because we just visited a new cell. Okay, so that's straightforward. And that's pretty much all you need with BFS. You need to find how do you get the neighbors. You need to find the state of that you will add to your queue, and then what you need to return once you reach your destination. And that's pretty much it. So let's just implement it and make sure it passes. Okay, so let's implement the solution we just saw in the overview. The first simple thing we want to do is, if the first cell is different than 0, there's no need to continue, because we know our path needs to go from the top left to the bottom right. If the top left is a non-zero cell, then there is no solution. The other case, if the bottom right cell is also non-zero, then we can't go there, and so there is no solution as well. Now, if there is no way to get a clear path, we want to return -1, and so that's what we'll do in this case. So we return -1. And now we want to create the setup for our BFS, so we need a DQ first, right? And then what's the initial value? Well, we said that the state of our queue is going to be the coordinates of the cell, and then the count so far, okay? So initially we start at 0, 0, and the count is just 1 because we count this cell, this top left cell, okay? And now we do our BFS where we go through and we pop. So this will give us I, j, and then the count. And then we'll visit the neighbors. And the neighbors we said in the 8th directions that we went over in the overview. So let's just copy the list of those. You could also, if you want, to just use a directions array where you just store what you add to I and j. That's also fine. But for now, let's just keep it like this. And then we want to make sure that these coordinates are within bounds. So let's call this the number of rows, and then this column needs to be within the number of columns. And so we need to define the number of rows and columns, which is, for both, it's just n, because this is n by n grid. And so we can just put n here. The other thing is, remember, we want a clear path, which means here we want the value to be equal to 0, because we will traverse only cells that have value 0. And so now we want to append to our queue, we want to append this and I and j, right? But we also want to increment the count by 1 because we just visited an additional cell, okay? And at the end, we want to return something. But first, we want to check if we reached the destination we are looking for. We should stop and return the count. What's the destination? That's just the last row, and the last column, so the bottom right, which is going to be at n-1 in index for I, and then n-1 for j, right? And so here we want to return the count in this case. Now, if we go through all the different possible paths or the different possible clear paths, and we are not able to get to the bottom right, cell, then we want to return -1. And so that's what we do here. And now there is only one thing remaining, which is, you notice here we didn't mark visited set, so we'll get time limit exceeded because we can visit a cell multiple times. There is nothing to prevent that. And so let's just create a visited set so that we don't do that. And then here we want to add the first visited set, which we already added to the queue, so 0, 0. And now here we want to add that we visited this cell in I and j because we added it to the queue. Okay. And now here we need to check, before visiting a cell, we want to check that it's not in our visited set. Okay. Now, if you, there is a variant solution where you could put visited add here for I and j, but if you do that in this specific case, you will get time limit exceeded because you will for cells that are already visited, you will still enqueue them in the queue. So you will incur the cost for all of them, and you don't need to do that, right? If it's you don't need to add it if it's already visited, right? And so we should do it like this. And so we should add it like this. And now, yeah, we should remove it here. And now this should work, so let's run it. And it looks like it passes. We can submit. There is one wrong test case here. Yep, sorry, there is a mistake here. We should check this neighboring cell and not the initial cell. Yep, so we have another mistake here. If either of these is different than 0, we don't have a solution, right? We shouldn't check n because maybe only the top left cell has value 1, and that still means we don't have a valid path, right? And so we want to check if it's different than 0. And then we can run this, and looks good so far. Let's submit, and that passes our that passes here. Now, a slight modification, if we don't want to have this cost for this extra space, there is another way to do it, which is instead of adding it to a visited set, we can actually just mark it with a different value, which is 2, for example. Because if we do that, or even you could use 1 if you want, because if you do that, then this check here will always fail, which means we will never add it again to the queue. And so that's another way to do this. We can remove this now, and we can remove it here. But for this cell here, we want to also mark it as visited by setting the same value so that this check will never pass. And so to do that, we'll just set this to 2, remove this, and this should work. Let's submit. And it does, okay? Yeah, and so that's pretty much it for this problem. Now, in terms of time complexity, this is going to be just BFS, which is going to be O of E plus V time. Now, what is V? V is just the number of nodes. So how many we have? Number of cells. We have n squared. Now, how many edges we have? Well, we have 8 for each cell, and we have n squared cells, so we have 8 n squared. So roughly, it's similarly O of n squared time. Space also similar because we will add all the cells to the queue at most, so it's also of n squared space. Yeah, so that's pretty much it for this problem. Please like and subscribe, and see you in the next one. Bye.